Hey everybody, we're going to have a look at similar triangles today. And I'm going to start off with this triangle here. And you're going to notice that if I copy and paste this triangle like so, then we get two triangles that are identical in their lengths and they are identical in the size of their angles. Okay, and we've already looked at this. This is a term that we call is congruence. Okay, we would say that the two triangles are congruent when they have the same lengths and when they have the same size angles. And today we're looking at similarity. So similarity is when we have the triangle, which I'm going to start over here, and then I'm going to manipulate the triangle a little bit. If I grab the corner, not the side or the top or the bottom, but I'm going to grab the corner and I pull it out. And I'm sure you've all done this. We now have two triangles that they look the same. They are in proportion with each other. It's just bigger. Okay. And what's happened? Has the lengths changed? Yes, they have. So we would say that they have different lengths. And tell me about the angles. Are they different as well? And we would say no, they still have the same angles. Okay? And so that is similarity versus congruence. So let's have a look at the first rule. Okay, let's say I've got a side here of 5 and a side here of 5 and a side here of 6. And on the bigger triangle, if this were 10, and if this were 10, and if this here, the base was 12, then we would say that these two triangles are similar. Now, what is our scale factor? That's another really important term you need to know. Scale factor. In other words, how many times bigger is the image? Remember, we call this the original, and this one is called the image. How many times bigger is the image? Hopefully you can all see that it's a factor of 2. Okay, so 2 times bigger. So is that consistent across all sides? 5 times 2 makes 10, yes. 5 times 2 makes 10, yes. And 6 times 2 makes 12. All three of them satisfy the same scale factor. So we're going to say it satisfies the SSS rule because all the sides are in the same ratio. And that's the key here with similarity. They all have to be in the same ratio. All right, let's have a look at the SAS. With the SAS, we have one side that has a scale factor of 2. 5 times 2 makes that 10. We have a second side, 6 times 2 makes it 12. And the the angle that is between the two sides are both equal. They are the same angle. Okay? Angles never change with similarity. So in this case, we have the side angle side rule, where the sides have to be in the same ratio. The angles need to stay the same size. With the RHS rule, okay, we need a right angle. In this example here, I have a 90 degrees, and down here I have matching 90 degrees, which is good. So we satisfy the R in this case. Then we need the hypotenuse in the same ratio. So up here I have 12, and over here I would need the hypotenuse to be in the same ratio. Now, what is the scale factor in this case? Well, here I've got a 5, times that by 3, and I get 15. So in order for this triangle to be similar to the original, I would need to take this 12 and times it by 3. This would have to be 36. And if that is the case, then it satisfies the RHS rule, where the sides are also in the same ratio. Okay, finally, the fourth rule for similarity is actually not the AAS rule. It's actually AAA. All right, let me explain that one. Let's say that these two triangles have a 90-degree angle each, and they each have 60 degrees. Well, then it's safe to say that the third angle would have to be 30 degrees. We can solve that using arithmetics. And so this angle true would also have to be 30 degrees. Now, if both triangles have 3 matching angles, then the side lengths are pretty much irrelevant because these two triangles would have to be similar. Okay, so this is the fourth rule for similarity. Okay, so let's have a go at some questions.